Hello, pre-calculus students of Mad High and South Texas College. We are approaching the middle of our last chapter, still in Chapter 8, Applications of Trigonometry. The last lesson you did, without any help from me, you were on your own, and you did really well on the assignment overall, all three classes. I actually think some classes had a better average by me not teaching. I wonder if that's a message to me. But anyway, you already went through vectors and talked about it geometrically and did all the terminology about what a vector is. 8.4, we repeat it in a way, but we're going to apply probably a little more algebra definition to it. Some of it might seem the same. We are going to add them, vectors. We're going to subtract them. We're going to multiply them by scalars. Those are numbers. We are going to do a multiplication of them, which is called a dot product. And we'll use vectors to also find the angle that is in between two vectors. So that ought to be really fun. Enjoyed this. I actually enjoyed doing the algebraically defined vectors and the dot product. I hope this trip was as fun for you as it was for me. Talk to you later. Be well, be safe, take care of yourself, and take care of others. Over and out. As you know, vectors have a starting place, and the initial point, if it's at the origin, in other words, if you take just some vector that's out in space out here, let me call it here, there's a vector out here, and let me call that, vector W. If I was to have some sort of magical way to take this vector, let's see if I can make it happen here. Wouldn't you know it, when I want to move something, it won't let me move it. If I was able to slide this vector down, it's not letting me do it. I almost did it. Try it again. Take this vector and slide it straight down without turning it and moving it to the origin. That would be a position vector. It's starting at 0, 0. Okay. We usually name the vector when we are talking about these position vectors. Let me get rid of this junk. Oh, that didn't work. That worked. Okay. That moved again on me. There, we put that back here. Okay. A position vector, we name it by where it ends. So all our position vectors start at 0, 0. All our position vectors start at the origin. And it ends, that's its terminal point. Then if it ends at some sort of A comma B, we say this is vector AB. When you see this, and let me call that vector, he's calling it U. When you see it, you always know it's starting at 0, 0. And it ends at AB. Position vector, initial points at the origin. Good lesson. The A is considered a horizontal component. The B in this case, the second value, is its vertical component. So it basically tells you where you are in the coordinate plane. And so no matter what I give you, if I say K is -3, -7, then all you really care about is where's -3, -7. And then you will go from the origin and you will connect it there. And that's vector K. I should have put brackets. That's the convention. Brackets, not parentheses that we use for ordered pairs. When you have your angle, the positive angle between them is called the direction of that angle. Direction of that vector. So open up to a positive degrees. Let's just pretend it's 30. That's its direction. That means you are guaranteed that if I just told you I have a vector and its direction is 30 degrees, you can guarantee that all I have to do is find positive 30 degrees here, and I know the vector is going that way. I may not know the magnitude of that vector, how long that vector is, but I'm guaranteed at least I know where the direction is. In this case, this positive angle could possibly be 200 degrees. So if theta is 200 degrees, then I can guarantee that at least I know that I don't know how long the vector is, the magnitude, but I do know which way it's going. That's called its direction. So finding the magnitude and the direction are very important. Now remember, this is all talking about the position vector starting at 0, 0. If I go back and let you look at this was all right. So the two things that you want to be able to calculate right now is magnitude and direction all the time. We're doing a magnitude the other day when you were taking two vectors and basically putting them together to create the magnitude of the resultant vector. This is a little different. See, we're actually going to say, I want to find the magnitude. And just think about it here. We go back to this one that we drew on the other page. This vector here. And if I know it went to, let's say, 3, 5, and I can actually put a point, but the thing is, vectors have direction, so we put an arrow to also simulate that that's the direction. And if I know this at 3, 5, then just pretend that it's our right triangle, this value being 3, this value being 5. How would I find this becomes a right angle? How would I find the length of this? It's a hypotenuse of this right triangle. So we do know that 3 squared plus 5 squared has to be whatever, I'll call it C, has to be C squared. So C has to be the square root of 9 plus 25, just like before. But C is actually a vector. So we use these absolute value symbols to represent that it's a vector. And that's a magnitude of the vector. Okay. There's other symbols that other books have used. This is what our book is doing. So that's why when you look at this, it looks exactly what I just did. A squared plus B squared square rooted, right? That's what that is. So the magnitude of vector u is nothing more than using the Pythagorean theorem of the two sides of a triangle that get created. And looking at that same picture, if I need that angle, what did we learn before about finding that angle? Well, I have two of the sides, so the trig function I would use is tangent. So we know that tangent of theta must be opposite over adjacent, which in this case is 5/3. So let me write that again. Tangent of theta is 5/3, but what I really want is theta. So I arctangent both sides to get rid of tangent. That gives me theta is the arctangent of 5/3. Tangent of theta, b over a, where a is not 0. So we'd solve that for theta, and we would get the direction angle. Not too bad. This stuff kind of, I actually think this section is probably nicer than the last section, because you may never have talked about vectors before, so you're like, what the heck is that? Example 1, he gives us a vector, 3, -2. He wants us to find the magnitude and the direction. I will warn you, direction always has to be a positive angle. So let's see what happens when I work with this, find the magnitude. The magnitude of u, this would be magnitude of u. And since u is boldface, that's his symbol for its being a vector. Some books do this, u, and they put a little hat over it. And that's called vector as well. But this book uses the boldface u, so I'll just stick with its connotation, the u. Magnitude of u is the square root, and I don't have to draw the triangle. I know one of these is A and one of these is B. Just go ahead and look at it. One of these is A and one of these is B. One of these has to be the one number, one of these has to be the other number. So if all I'm doing is squaring 3, why don't I just say 9? If all I'm doing is squaring a -2 and negative times it is positive, just put a 4. So we know the magnitude is the square root of 13. And the direction, well, we know that the tangent of theta has to be, now this is sort of important. You do need to know which A or B goes in the denominator. Well, if you always notate your B as the y value, like I just did here, then you know that, well, in this case, you know that this is theta, AB, opposite over adjacent. So B over A, in this case, would be -2/3. Theta is the arctangent of a -2/3. So let's go ahead and let's use our calculator and pause it right now, because I'm going to go and do my calculator, and I'm going to unpause it. It's going to look like I did it in the speed of light. Okay, I'm back. I got theta to be a -33.7 and some change, and he's been using the degrees. And I'm also happy, except for, what did I write up here? Positive. So what he did was, because of this being 2/3, the arctangent of 2/3 end up being a negative angle, because tangent has to do with these two quadrants, right? So it's going to give you one of those answers. And it gave me this one. So what I need to do, I need to take this angle and say, instead of going down this degrees, -33.7, let me start here at -33.7 and go all the way around and add 360 to it. That gives me the same position, same direction, but it went in the other direction. So theta will actually be -33.7 plus 360 degrees. That equals, okay, get your calculator out. I'd like to do it in my head. I almost can. I know it's less than 330, but let me go do my calculator. Pause it, you do it yourself. 326.3. Let me do it the right color and everything. 326.3 degrees. I hope I'm right. Rounded to the 10th. Questions? Of course not. Most of you guys did really well in the last lesson because all I gave you, I didn't give you any of my work, any of my beautiful work, which also meant I didn't give you any of my mistakes either. So you just went right to the answers and studied it. Or you went to my math lab and told them to tell you how to do every problem. Or you told them to give you an example, or whatever the case. Or you used all 3 or 4 opportunities to finally get it right. Whatever it took, as long as you learned it. My work looks pretty good. Okay. As I mentioned before, when I have a vector starting at the origin, and I said to you that this A is a horizontal component and this B is a vertical component. Doesn't seem to be too crazy. And you can represent vector, if I call this vector U, it can have a magnitude. Of course it has a magnitude. That's the magnitude is the length of this vector till it stops here. Even though I got an arrow, I'm still talking about stopping here. You can represent your direction angle by using sine or cosine. That should not be a surprise to you, because if this is theta, sine of theta would be opposite. In this case, opposite is my vertical component, which is labeled as B, over the hypotenuse. The hypotenuse is the magnitude of vector U, so magnitude of U. I could also say that cosine of theta is the horizontal, the adjacent, over the hypotenuse, so that would be A, the horizontal component, over the magnitude of vector U. So cosine deals with the horizontal component, sine deals with the vertical component. Now that you know this relationship, if you solve it for A and B, well, I'll do A first. A is equal to the magnitude of the vector, always times, I don't know why I put two, magnitude of vector U times cosine of theta. B will always be the magnitude of U times the sine of theta. So if that's A and B, I can represent my vector as magnitude of U cosine of theta, comma, magnitude of U sine of theta. And if you wanted to go further, you could factor out the magnitude of U times cosine theta, comma, sine of theta, which could be very, very useful. That's just a scalar. You can always multiply a vector by a number. This is a scalar, this is the vector. Okay? A cosine of theta times its magnitude. Example 2, vector W, that must be vector W right here, has a magnitude of 25. He already gave me the magnitude. And it gave me the direction, 41.7 degrees is a positive angle. Find the horizontal and vertical components. I just showed you a minute ago that A, this horizontal piece, is always related to the cosine of theta times what? Let me go back. I can put the magnitude anywhere I want. B will be the magnitude times sine of theta. So if I want the two vertical components, that's A and B, A will be, let me just type 25.0. That doesn't mean there's no decimals. There could be other decimals after the 0. He's just rounding it to the 10th place. 25.0 cosine of 41.7 degrees, and b would be 25.0 times the sine of 41.7 degrees. Each of these requires a calculator answer, and we will round that answer to the tenths because he did for this one. Pause, type it in your calculator, make sure you know how to get the answers by yourself. 18.7 is one answer. Let me go do the other. 16.6. Now, this actually is vector W in component form. So I can actually say W is this vector. Because vector does just list, you can list it by its component. 18.7 comma 16.6. Well, I think that's exactly what happened. That would be the ordered pair you're at. That would be the ordered pair you're at. 18.7 comma 16.6. So that's vector W. Okay. A, B, plug it in, did the work, there it is. And so I already told you they were horizontal, and horizontal is always and vertical is always. We have example 3. I did not make a copy of it. Oh man. Okay, well, let's just look at the solution. Write each vector in the figure. Okay, I know I didn't look at it because my computer didn't have the fonts. So it should have been, those symbols here means vector. In case I miss it somewhere else. Okay. Write each vector in the form. So he's just telling me if I'm doing U. Now this is the answer. So he did all the answer. You have to look at U. U is this 60-degree direction, and this magnitude goes out to here. Now I don't know what the components are, so let me open it up over here. 60. We know it's 60. I drop that down. You stopped right here. I do see a number 5. I think, like I see it here, but I'm not sure if that applied to. I think he's labeling that as a magnitude. Because I see this going out here and he's calling it a 2. It looks like it could be a distance of 2. Yeah, I think these are magnitudes. Okay, so if this distance here, I would have wrote it here, 5. So I don't know what A and B are. But we can easily do the work because A will be 5 cosine of 60 degrees. B will be 5 sine of 60 degrees. And we learned a long time ago that 60, and that's 1, 2 square roots of, 1, 2, yeah, square root of 3. That works. So cosine of 60 is 1/2. 5 times 1/2. Sine of 60 would be square root of 3 over 2 times 5. Square root of 3 over 2 times 5 is 5 square root of 3 over 2. So vector U is this vector here. 5/2, comma, 5 square roots of 3 over 2. If we were to work on vector V, okay, vector V is kind of interesting. This now is my A. A is the same as the magnitude of the vector. that A component, well, let's just do it. Let's just do it. You're going to see it. Is 2 times cosine of, what's that angle? It's 180 degrees. B is 2 sine of 180 degrees. Cosine of 180 is the -1, as you recall. -1 times 2 is a -2. Interesting, see? 2 on the left. Now, sine of 180 is a 0. So 2 times 0 is 0. -2, 0. Well, that looks like the ordered pair, doesn't it? -2, 0. So vector V, how did I write the other one? Did I write it with a, I wrote magnitude. That isn't right. It was just U. It's not magnitude of U. U. I could have put a little vector hat. Sometimes that's what I told you some books do. But he uses bold font to say it's a vector. So you could use bold font, or you could use little tiny hat and say vector V is going to be, the components are -2, 0. Last vector, the green one. We do green. If I drop, I need this angle. Okay, so I got to go. I see he did a 280, starting from here, 280. But that's the positive angle, so that's the angle I have to use. Okay, so the A, there it is. It's going to be A, B. Here they are. So A will be, that magnitude is 6 cosine of a 280 degree angle. B is 6 sine of 280 degree angle. Let's see. I don't know what that is in my head because the reference angle is 80. This is a -80. I mean, it's a -80 degrees. Or is it? No. Yeah, it is -80. So I'm going to use a calculator. Oh, I don't have to. I have the slide right here because he did all the work. Let's see. Let's check our other work if we're right. I said did I say 5/2? Yeah, 5/2, and then I did did 5 square root of 5/2. Yeah, that looks good. V, -2, 0, got that. And 6 cosine of 280, 6 sine of 280, that's exactly what I said. Here's his magic answers. So I'll take his word for it. We could have paused and gone to the calculator, but oh well. Copy of it. Vector operations. Just like you have operations all the time. Polynomials, what can you do? Can you add polynomials together? Can you multiply polynomials? It's same thing. Can you add matrices? Can you subtract matrices? Can you multiply matrices? They just sometimes have a different procedure. But there's no problem with adding two vectors together. When you add two vectors together, all you're doing is adding their horizontal components together and adding their vertical components together. If you take a vector and you multiply it by a scalar, a number, it's the same thing as distributing this scalar inside of both pieces. You saw me earlier pull out the magnitude of a vector. That was the same thing as pulling out the vector, the scalar, and saying A comma B. I did that in reverse. If you have a vector U and you want the opposite of that vector, then you would have to take the opposite of each horizontal and vertical component. That's kind of weird. Is it AA? If you take a vector, and let's see here, we're subtracting another vector. Well, it's not much different than the addition one. It would be a minus c, there it is. B minus D, there it is. He kind of made it a little more complicated. He distributed the negative like we would have done and make it a plus. Same thing, distributing it, and so it's the fancy way. To remind you, so knowing those properties, and he has vector u and vector v. See how they're very bold face? That's how I know they're vectors. So u is this little one over here. And v is this little one over here. And if you're going to illustrate the following, what am I illustrating? I guess I must have erased something. He's doing u plus v. In other words, vector u plus vector v. You did this before, as you recall. You used the parallelogram principle, I believe, where you took this diagonal, this vector, and made it parallel to here, and this vector parallel, and you connected those two. Yeah, that's what you did in the geometry. And that's fine. But what we're going to do is we're going to find out what that vector is without having to do that work. So I hope you're ready. That is equal to negative 2 plus the 4, comma, 1 plus the 3. The resultant vector that you get when you get done should be, and vector u plus vector v is going to be vector 2, comma, 4. Just adding those up. So I go to 2, comma, 4, and if you draw the position vector to it, then what you just basically did was you can now find that magnitude if you have to, because you know what those numbers are. The magnitude, what did I write that for? You can do a lot of things. The magnitude of u plus v would be the square root of 4 plus 16, square root of 20. So I know how long that is. But this should look very familiar. Oh, all he was looking for was that. Got it. Because I have... Oh, it was A. I erased his problem is what I did. Oh, well. Oh, okay. See, I must have missed something. And I must have erased it B, because I don't see B either. B, C. It can't be much different. 3u minus 2v. So technically, you're doing 3 scalar outside of negative 2, comma 1. Then you're going to subtract it 2, or plus negative 2, and call the negative 2 the scalar, but it doesn't change anything. Try to keep it similar to what we've always done mathematics. You have to multiply the vector by the scalar first. That gives that vector as negative 6, comma 3. And you're subtracting the vector 8, comma 6. And when you subtract a vector, it's adding, you're distributing the negative. Bottom line is the vector is negative 6 minus 8, negative 14, comma 3 minus 6 is negative 3. What does that mean? That without even looking at this picture, I know that my resultant vector is left 14, down 3. So there's my position vector. There it is. See? Left 14, down 3. And let's see how this worked geometrically. Let's just play around with it. My original vector u was negative 2, 1. Negative 2, 1. There's my original That's not it. Negative 2. Well, it's not on there. Negative 2, 1 doesn't appear to be there. What he drew was 3 of negative 2, 1. Negative 2, 1. Negative 2, 1 was here. That's the how far my original vector went. Then my original v was 4, 3. 4, 3 was right here. This is my original v. This is my original u. What he did was he drew the scalar multiply. 3 of these and 2 of those. 2 of those and 3 of those. That's fine, okay? Then what's interesting is, look what he did here. This was a minus 2 of these. So when you put a minus in front, opposite vector of this one was, there's my 2v. To do the direct opposite would be to flip this over the origin and go the other way 2v. There's your negative 2v. So now you look at my problem. I have 3 u's plus a negative 2v. I have 3 u's right here, and I'm adding it to a negative 2v's. The resultant vector, that vector that's in between, that equilibrium state, is this particular parallelogram that you made from lesson 3. So that's the vector that we're talking about. And how would I find that vector? Well, we found it by, in this case, adding the horizontal components to a negative 14, adding the vertical components to get a negative 3. Isn't that cool? Don't all get excited at once. Of course, we haven't found the magnitude, though. I haven't found the magnitude of 3u minus 2v. But that's a piece of cake, because that's just the square root of the components that I had. Let's see, I had 14 squared is, oh, goodness gracious. It's 14 times 14. Is it, I better just write out. My brain burp. I don't want to even say it. 16, 4, 5, 4, 1. Yeah, that's it. 196. So square root of 196 plus 9. If you had to do it, 196 plus 9 is 205. Square root of 205. If you had to do it. All right. Let's see if we're right. Well, yeah, of course we're right. I had the picture on the other screen. Duh. Okay, another vocabulary word, a unit vector. Unit means 1. So it's any vector that has a magnitude of 1. It can be going this way, length of 1. It could go up, length of 1. It could go down, still starting at 0, 0, of course, length of 1. It could go left. It could also go out any direction, length of 1. Doesn't matter. We call the unit vector, and he's using I and J mode. He's calling vector I. Usually you have like X, Y, and Z. X, Y, and Z. I, J, K. If you're using 3 dimensions, which, believe it or not, you can do vectors with 3 dimensions. I don't think we'll get there. I don't think so. And then so IJ stands for the X and the Y, the horizontal and the vertical component. Obviously, this is 1 comma 0. 1 over, don't go up. This one obviously is don't go over but go 1 up. Okay? Any vector can be expressed in the form of an a times an I plus a b times a j. Because it's just saying you can multiply anything by 1. And it doesn't change it. So I go over a direction and I go up b direction. I can say 1j, or in this case, I went 3 to the right. So I can go 3i. I can add that to 4j. That can be my vector u. 3i plus 4j. That's another way of representing a vector. It's the same. It's still this 3 comma 4, but now I say 3i plus 4j. It's the same thing. Just another way that, you'll see it maybe in physics. Okay, if vector v is ab, then ai, okay, what I just said. Where obviously I is 1, 0. Think about it. If you take a and you multiply it by the vector 1 comma 0, and you add it to some b number times 0 comma 1, both of those being unit vectors, one going to the right and one going up, and I multiply a times 1, that gives me a, and a times 0, that gives me a 0. Well, so that's vector a0 plus b times 0 is 0, b times 1 is b. Add the two vectors together. A plus 0 is a. 0 plus b is b. Da-da! The same thing that we started out with. So you are allowed to multiply your scalar, your horizontal value, your horizontal magnitude, your whatever you want to call it, my vertical times a unit vector to get back to the same vector that I did before. How do you multiply vectors? It's called a dot product. And when you multiply two vectors together, you don't get another vector. You get a scalar. You get a number. And to multiply two vectors together is really quite simple. You take each horizontal component and you multiply them together, a times c, and you add that to the vertical components multiplied together. So u dot v is AC plus BD, because you multiply your horizontal, you multiply your vertical, horizontal, vertical, and you add that together, and that gives you a number. A number. It's a value. You don't get a vector, you get a number. Back to the beginning. It's simple. Piece of cake. When I dot, see the dot? Will be, why am I putting a vector there? I just got done telling you there's no vector there. Listen up. It'll be 2 times 4, 8, plus 3 times a negative 1, negative 3. That answer is 5. 6, 4, dotted, negative 2, 3. 6 times a negative 2, negative 12. Plus 4 times 3 is 12. That one's a 0. Okay, just a value. You learn this because you use this skill to find the angle between two vectors. I'll give you that formula in a minute. Let's see. Yes, I did. I'm scrolling right. 5 and 4, is that what I had? All right, see, I already forgot. See how old I am? I already forgot. That's where. Properties of the dot product. They look so familiar. U dot V is the same as V dot U. In other words, it's commutative. Commutative. U dot V plus W looks to me like what? U dot V plus V dot W looks a whole lot like distributive, doesn't it? U plus V dot W is the same thing as U dot W, V dot W, and well, that's the same thing as distributive, just the other way around. K times U dot V is the same thing as KU dot V because I could have pulled the K out. So K outside of U dot V is the same thing as K times U dot, it looks like this, KUV. Looks the same thing. They're just, that number is just in there. Okay, but what was he trying to show? He was trying to show that KUV is equal to a U K times V because it doesn't really matter U times, I said dot, I should say dot product. Doesn't matter where the K goes. It's kind of like this. 3 times 2 times 5 is the same as 2 times 3 times 5, which is the same as 5 times 3 times 2. All those things just keep changing around. And if you take a vector and you dot product with 0, you get 0. And if you take a vector and dot product with itself, all it does is give you the magnitude of that vector squared, what makes sense. It does. I mean, here's my example. 2, 2 dotted with 3, 3. See, 2 times 3 is 6, plus 2 times 3 is 6. Well, it doesn't make sense to you, but that's what it's turning out, is 12. That would be the magnitude. Let's see, can I... magnitude of u squared. Magnitude of 4 plus 4. Well, that's mathematically correct. 6 plus 6 is 12. There it is. Just didn't look right. Geometric interpretation of the dot product. The whole reason that you learned a dot product is to find the angle between two vectors. Now, obviously, we're talking about two vectors that are between 0 and 180. Because cosine deals with these two primary quadrants. And so, dealing with this, the cosine of theta, that's the angle that's between two vectors, that's this angle here, is equal to dot product, this is u and this is v, you dot product the angle, the vectors, then you divide by the product of both magnitudes together. So you probably want to write that down and memorize it. And let's practice it once. Find the angle theta between two vectors. So let me draw them first. 1, 2, 3, 1, 2, 3, 4. So there's my vector u. 2, 1, 1, 2, 1, 2, 1. There's my vector v. And I'm looking for this small angle right here. Good luck. Okay. Normally that'd be a very hard problem to use just with trig. For one, it's not a right triangle. I'd have to use, I could use, I I could use probably law of cosine. Probably could. I'd have to find. That's too many unknowns. Might be too hard. Let's use our new technique. That the cosine of this small angle will be equal to, I'll write it all out, uv, that would be vector 2, 3, comma, 4, dot product with vector 2, 1, over the magnitude of u times the magnitude of v. I should have worked it out, but I wanted you to see it. So let's go to dot product, those two. That's just going to be a number. 3 times 2 plus 4 times 1 over the magnitude of u would be 3 squared plus 4 squared, square rooted. 3 squared plus 4 squared, square rooted, times the magnitude of this one would be a 2 squared plus 1 squared, square rooted. 2 squared plus 1 squared. Okay. 3 times 2 is 6, and that's a 4. That's 10. 10 over, and this is, did I write it right? It was supposed to be 4 squared, right? 3 squared. 4 squared, yeah. Why did I put a 2 there? It was a 3 up there. 9 plus 16 is 25. Square root of 25 times. And this one here is 4 plus 16, isn't it? No, it's a 1 squared. Can't read my handwriting. That was a 2 and a 1. So that's 4, that's square root of 5. Equals 10 over 5. Still times the square root of 5, which I don't know. So cosine of theta is 10 over 5 square root of 5, which is 2 over square root of 5. Got to pick up my calculator and do the arc cosine of 2 over the square root of 5. And I need a positive angle. So pause it. Let's see what we get with our calculator. 26.5650 degrees. Round that to, let's see. I don't know what he's going to use. I'll just take 26.6 degrees. Yeah, that angle's actually a lot bigger than I thought. Let's see if we're right. Less. Dot product, magnitudes multiplied together. Okay. 5. He did 2 decimals. That's fine. No problem. Next problem. Find the angle theta between 2 vectors. Okay, let me draw. Because inquiring minds want to know. 1, 2, 1, 2, 3, 4, 5, 6. That vector goes from 0, 0 all the way to here. That's vector u. Vector v is 6, 2. 1, 2, 3, 4, 5, 6. 1, 2. Vector goes here. And that is a lot bigger than I had on the last problem. But we won't let that fear me. Still, I'm looking for this angle here, theta. Cosine of theta is equal to, let me just do the work, the two dot products. 6 times 2 plus negative 6 times 2 over 1 square root will be 2 squared plus 6 squared, because the negative doesn't matter. 2 squared plus 6 squared is 4 plus 36, that's 40, times square root of 6 squared plus 2 squared, that's 36 plus 4, again 40. That turns into 12 minus 12 over the square root of 40 times square root of 40 times square root of 40 cancels out the square root. So that's not that it matters, because 12 minus 12 is 0 over 40, which is 0. Cosine of theta is equal to 0. Do I really need to go to my calculator? Cosine of what is 0? Cosine is not, this is a 1, this one's a 0. What angle is that? Theta is a 90 degrees. And if you look very careful, look at, my picture was almost perfect. 90 degrees. There's a name for these two vectors, in case you haven't had physics. These two vectors are considered orthogonal. Orthogonal. Which means they're perpendicular. Perpendicular. Anything is perpendicular if it makes a right angle. Wonderful. And for angles theta between, by the way, that 90 degrees is between 0 and 180, just saying. Angles theta between 0 and 180, the cosine of theta is always positive. If it's 0 or negative, then theta is less than or equal to greater than 90. Here's a chart. When you dot, it's because when you dot product acute angles, you're going to get a positive number. When you dot product two vectors that are right angle, is that a right angle? You'll get a 0. The dot product will be a 0. So it happened to us. If you dot product the angle and it's going to be bigger than 90, obtuse, your dot product will be negative of this. If u dot v is 0, which is what we had for two non-zero vectors, and v, then the cosine of theta is 0 and theta must be 90, we say that u and v are perpendicular or orthogonal vectors. Thank you very much for that. And that is the end.